Hello, everyone, and thank you again for joining us today for our latest HashiCorp snapshot titled How a Shared Registry Enables an Enterprise-Grade Service Mesh, which will be presented by Tony, our Senior Solutions Engineer at HashiCorp. So today, Tony is going to show you why a registry matters and how it supercharges a service mesh like no other. Now, before we get started, I just wanted to go over a few housekeeping items. First of all, I would like to note that this session is being recorded and the recording will be made available within the next day or two. We will send you an email with the link. Secondly, please submit any questions you have throughout the demo by Q&A tab, and Solution Architect David, along with Tony himself, will answer them as we go. So with that, let's go ahead and get started. Over to you, Tony.
Thanks, Khalees. So first, what is Consul? At its core, it is a service network solution that enables organizations to discover and connect applications and services running across multiple environments. And Consul maintains a registry which provides an up-to-date list of these applications and services that are deployed in your infrastructure and the health of them. Now, we've probably seen this diagram many times before, but today let's take a services communications view. Services typically need to call one another, and with the monolithic applications, services invoke one another through language level methods or procedure calls. However, a modern microservices application typically runs in a containerized environment where the number of instances of the service and their locations change dynamically. We can also call this transition traditional to modern or static to dynamic. Now, the problem in the context of microservices is discovery. How does a service discover the location of another service? Within a single cluster, this might be okay. But we find enterprises will have a lot more than a single cluster with services spread across them. So how are these services aware of each other? The number of these service instances and their locations change often and dynamically. The services are usually assigned a dynamic IP address. The number of services, for example, adjust. Auto scaling groups might increase them based on their load. Consequently, you must implement a mechanism that enables the clients or the service to make requests to a dynamically changing set of ephemeral service instances. This is where a service registry comes in. So services register themselves with Consul's registry as they come online. They also deregister themselves as they are destroyed. The registry becomes this source of truth about the service. It contains information around its location, its address, its health status. We can even associate custom metadata and tags. In this example here, the public API service instance comes online. It registers itself to Consul. In this case, we have multiple for resiliency. The front-end service is leveraging DNS, and it's using public.service.consul to reach the public API service. In this case, the front-end service will query that DNS record, public.service.consul, and Consul will return the closest instance that is healthy. And then the front-end service will then communicate with that returned address as per normal. This is all happening without a load balancer. So if we had instance 2, for example, become offline or become unhealthy, the query will return the next available instance. It could be instance 1 in this case. So health checks can be customized to suit a particular service. We can do TCP checks. We can do custom script checks. We can leverage the native Kubernetes health checks as well if we're speaking about containers running on Kubernetes. Now, the discovery mechanism works through the API or DNS. DNS is great because we know it scales and it works with the majority of application and implementation and custom environments. So what's this got to do with a service mesh? Well, using the registry with each service, we can deploy a sidecar proxy. In this case, we're leveraging Envoy. Envoy is a modern, high-performance, small footprint service proxy. And what Consul does is configure Envoy's XDS API using the same discovery goodness we just spoke about. We're going to go through some of the primary use cases organizations adopt service mesh, or why they adopt a service mesh. And the first use case is security, which is part of the zero trust model. Through Envoy, this allows services to communicate with each other securely. It works by using a TLS certificate as an identity of that service. The certificate is then used to establish or accept connections to and from other services. When both services mutually authenticate, we then guarantee the traffic is encrypted. Consul also ensures service-to-service permissions through intentions. This is access control for services. What services are allowed to communicate with what? Another use case is traffic management. This enables operators, application development teams to leverage capabilities such as traffic shifting. It allows for various deployment strategies such as blue-green, canary, and others. Another capability is circuit breaking. This is an important pattern for creating resilient microservices. It allows you to write applications that limit the impact of failures, latency spikes, and other undesirable effects. Consul has the ability to manage layer 7 traffic. Another key use case is observability. As workloads transition to microservices, observability becomes a necessity. It empowers operators, app dev teams to troubleshoot, maintain, and optimize their applications they're building. There are typically 4 golden metrics that are associated with microservices and service mesh technologies. They are latency, and how long it takes to receive a reply for a request, traffic, how much demand the system is under, such as requests per second, errors, what percentage of the requests result in an error, and saturation, how close the available resources like processing or memory are to be fully utilized. So there are some of the key drivers why an organization would adopt a service mesh. Now that's well and good. Those use cases add significant benefits to modern approaches and modern development. But how do we operate this at scale? And how do we meet enterprise requirements? Enterprises today typically have applications and services that run across multiple clouds. They could run across different Kubernetes clusters. They can consist of virtual machines, self-managed Kubernetes, or even public cloud ones like EKS or GKE. They could be consuming native services like AWS RDS, or even GCP's memory store. So we see a lot of this, organizations developing or refactoring services to microservices. And one of the key use cases for a service mesh like Consul, leveraging this registry that's keeping all this information about all the services that are running and operating in the environment, is to connect them together. So as these organizations are refactoring to microservices, we still see them have a requirement to talk to backend data. For example, customer data that was stored on premise, perhaps on an Oracle database. So one important use case is how do we allow these new services to communicate with those backend services, but apply those same service mesh principles consistently across them? Things like encryption, things like service-to-service permissions, and observability. So I have a quick demo today demonstrating Consul service mesh capabilities powered by the registry. This is HashiCorp's. It's our software ordering service. And I have an ingress gateway where users and consumers would access the front end. We have a number of services here. We have the front end being built by the GraphQL. That it then talks to the public API again, which is GraphQL. But then we have a products API, which is written in Go. We have a payments API that is Java Spring Boot, and they rely on different databases. The products API relies on a Postgres database. This one is built on a virtual machine, EC2 specifically, and then we have a Redis database, which is the payments cache, which talks to the payment service or is consumed by the payment service, which sits on GCP's memory store. We have two clouds, like you can see, AWS and Google, two VPCs. We have two Kubernetes clusters, one being EKS, the other one being GKE. They actually both have the same address space as well for their pods and services. So we have overlapping IPs. I have Consul deployed, which is federated together using mesh gateways. Mesh gateways allow control and data plane traffic to ingress and egress securely between the two environments. This dramatically simplifies the networking requirements. So we'll talk about traffic flow. The product's API service running on EKS as a container is communicating with a Postgres service, PostgreSQL service on EC2, being a virtual machine. We have the public API service, the payments API service, in this case, talking to the Redis service as its payment cache, and that's on GCP's memory store. What we have here is an application that is spread across two different clouds and platforms, containers, virtual machines, and a cloud native service being the Redis on the memory store. In the interest of time, I've deployed the two environments already, the two cloud environments. They both have Consul running in each data center, federated together using mesh gateways. This is actually quite a simple process, just using Helm charts. I already have PostgreSQL on the EC2 instance, and I already have Redis. What I don't have is any of the containerized applications running yet. Now, please reach out if you want more details on how I deployed this, or if you want to leverage some of the Terraform code that I used. So what I'll do now is just flick over to my demo screen. What we can see here is the Consul UI. There's a bunch of services already in there, like I mentioned, Consul being deployed, Ingress Gateway being there, Mesh, and this is the product API DB, which is my Postgres on my EC2 VM. So if I click into this, I can see the one instance being there. It's in the service mesh. There's a proxy deployed on it. I can see the node address as well, and I can see a bit of metadata tags I've used to associate the service with. If I click into that, you can see I've added a health check. So it's polling 5432 on TCP to make sure Postgres service is running. Now, if I go back, I can see my GCP data center as well, my Google data center. And similarly, I have the payments queue, which is registered. And you can see the node or the memory store endpoint there serving on 6379. And I'm running a check as well to make sure that's available. So if I go back there, you can see that the terminating gateway, which I've leveraged in this scenario to connect to my memory store, is linked with my payments queue. All right, so I don't have any other services there. So what I'll do now is I'll go back to the AWS services, and I'll just bring up my console here. And I'll quickly demonstrate that I don't have any other services or any of the front end, the public API or the payments or the product API service running here. So now I am going to deploy that. And what we'll start to see is the service populate in the registry almost immediately. And what's going to happen is the pod starts and the sidecar inject themselves. We'll see the services come online. Before they come online, though, they will check the health status as well. And in this case, we're relying on the Kubernetes health. So you see that they're coming up pretty quickly at the moment. I can see with my front end, I have two instances here for resiliency. If one of them had an issue or the health check didn't pass, this will be removed from Consul, and any services that rely on this front end for example, ingress, traffic won't be redirected to that instance. So again, this is part of the service registry's discovery mechanism that powers the service mesh. So I can click in there and I can see all the health checks are passing, which is great. Right, it looks like all the services are online now. And what I can do is I should be able to hit the front end here. As you see, this was when it wasn't online. And if I hit the front end now, I get my HashiCorp's front end with a bunch of coffee or a number of different coffees that I can order as well. So if I go to the Terra Espresso, for example, I can now put in an example payment as a test. And you see I'm successfully populating the Redis cache that's sitting on the other side. So again, this is how the traffic looks, just to kind of reiterate the public service where I've just entered some of the payment information. So I was hitting the front end, I was ordering a coffee, it was listing out the products that are in the Postgres database. But also when I put the payment service through, it is communicating with my Redis on the Google service across mesh gateways securely over the internet, completely encrypted. So a shared registry is what makes it possible to operate a service mesh across multiple clouds in multiple platforms. Consul is platform agnostic. It works across, a VMware environments, AWS and Azure environment, and across different types of platforms, whether it's Kubernetes, Nomad, OpenShift, and so on. It has this control plane which can be federated across and provide enterprise capability. Things like access control, telemetry, audit. We can operate that control plane through the UI like we've just seen, or through the CLI and the API. And it serves a number of enterprise use cases. Today, we specifically focused on the service mesh use cases and some elements of the service registry. So with that, thank you.